So I hope the recording has started. So today we are going to have a session on graph theory. So I'm going to basically brush up you all with the basics of graph theory. And yes, so let's start. So let's start with the. So basically, when we talk about a graph, it's like we want to represent something connected by vertices uh, through edges on a sheet of paper. So let's see how we can really use these kind of representations and how are they useful. So let's first understand what is a graph. So a graph is a triple VEG. It's a tuple actually, tuple of three different sets where V is a finite set whose elements are vertices, and E is another set which is disjoint from V whose elements are edges, and J is called the incident relation, is a subset of V cross E in which each edge is in relation with exactly one or two vertices. So when we talk about J, it's a subset of V cross E. That means it is a cross product. It's not a cross product, it's a Cartesian product from V to E, such that it's a set of elements. It's a tuple of elements such that the first element is from the set of vertices and the second is from the set of edges. And there cannot so each edge can be in relation with exactly one or two vertices. It can't be in relation with more than two or less than one, because if an edge is in relation with less than one vertice, that means it is in relation with no vertice, then it's not an edge. And similarly, if an edge is in it's not possible that in relation with more than two vertices, because an edge is either a loop, which means, as you can see in this figure, edge E7 is a loop. So it is in relation with only V4. Otherwise, it's a, it's a, it's connecting two vertices, two different vertices. So at the most, it can have it can be in relation with two or one vertex. So this is how we represent the set of vertices, V representing V1, V2, V3, V4 equal to E1, E2, E3, 4, and J is equal to V1, E1, V1, E4, V1, E5, V1, E6, and so on, corresponding to each edge and each vertex pair. Now, obviously, edge set has to be disjoint from the vertex set because edges are different terms than the vertices, so there cannot be any overlaps. So let's see few simple definitions. So edges incident with just one vertex is a loop. So E7 is a loop. E7 is the name of the edge which is looping across V4. E5 and E6, these are parallel edges because they are in relation with the same set of vertices. That is V1 and V3. So they are parallel, and graphs with no parallel edges and no loops are called simple. So this is a simple graph. And generally, we deal with simple graphs in our analysis because yeah, so we would continue and focus only on simple graphs. So this is a simple graph, and now it's very easy to represent a simple graph because you don't have to write down a vertex set and edge set. You can simply write down the edges as two element subsets of the vertex set. That is, you can write it in this way: v1 comma v2, v2 comma v3, v3 comma v4, v1 comma v4, and v1 comma v3. So this is the set of edges. It's simpler to represent the edges as we cannot have two different edges or two different edges representing uh, the Cartesian product of vertices. So v1 comma v2 cannot represent two different edges. Similarly, since there is no loop, I don't have something like v4 cross v4 comma v4. So representing edges is simpler with it's simpler if you have a simple graph, and we don't need any incident relation. So this type of a graph is called an undirected graph. So an undirected graph is a graph where there is no direction in which the edges are connecting one vertex to the other. So let me show you how will a directed graph look like. So if this is a directed graph, then this is how it will look like. Just that there will be a direction in which the edges will be drawn. So this is how you can represent a directed graph where a 1, 2, 3, and 4 are the vertices. So in this case, the edge is connecting 1 to 2. This edge is connecting 3 to 2. This edge is connecting 4 to 3, and this edge is connecting 4 to 1. So this is how a directed graph looks like, but we will only focus on undirected graphs. So let's move forward. So let's come to a few terms in graph theory. So they are a graph is empty. And in case you all are having any doubts, you can interrupt me anytime and ask me in case you are having some questions regarding these terms. So a graph is empty if there is no edge, if there is no vertex in it, and it is trivial if there is no edge in it. So obviously, if there is no vertex in it, there cannot be any edges in the graph. And if there is no edges, then perhaps a graph may look like this. That is a set of just vertex and no edges. So this may be called a trivial graph. Now, cardinality of the vertex set of a graph G is called order of G and is denoted by mod of G. Now, cardinality of the edge set is called size of G and is denoted by double mod. So for a trivial graph, cardinality of the edge set, that is size, is 0. And similarly, order of empty graph is 0. Two vertices incident with the same edge are adjacent or neighbors. So if we come to this example, uh, I hope it's visible. So it's, if you see, V1 and V2 are neighbors because they are incident by the same edge E1. So similarly, V1, V4, V4, V3, V2, V3, and V2, V4 also are neighbors to each other. So any pair of vertices which are connected by an edge will be called as neighbors or adjacent vertices. Now, similarly, two edges incident with the same vertex are adjacent. So, what does it mean? It means that, as in this example, E5 and E6 are adjacent edges because they are incident with the same vertex V4 and V2. So, edges which are connecting the same vertices are also adjacent. So, they are otherwise also known as parallel edges. So, parallel edges are adjacent edges. Let us also see a term called as degree. So a degree of a vertex is the number of edges incident with the vertex where you count the loops twice, and that is denoted by d of v or d subscript g of v. So as you can see here, the degree of V1 is going to be 2 because two edges E1 and E4 are incident with it. And similarly, degree of V3 will be E2, E3 and E1. This is E7. Sorry for the bad notation. So E3, E2 and E7, which is counted twice. So the degree of V3 is going to be 4. And similarly, degree of V4 also will be 4 because E5, E6, E4, E3 are incident with it. So the set of neighbors of a vertex V of G other than V itself is denoted by N of V or Ng of V. So the set of neighbors, meaning if you consider the vertex V1, then for V1, V2, V4 are the neighbors. Similarly, for V3, V2, V4 are the neighbors. So the set of edges, the set of vertices which are connected to it uh, through an edge directly, uh, will be a part of the neighbors of that vertex excluding that vertex itself. So even if it has a loop across itself, we won't count it as V3 is a neighbor of itself. So anything which is so anything apart from itself which is connected to it is going to be in the set n of v. Now, if U is a subset of the vertex set of G, then N of U is the set of those vertices that are not in U, but are adjacent to a vertex in U. So what does this mean? This means is that suppose U is a set of vertex, let us say V2 and V3. So if U consists of V2 and V3, then let us find what all vertices V2 is adjacent with. So it is adjacent with, let me use a different color. So it's adjacent with V1, it's adjacent to V4, and V2 is also adjacent with V3. So it's adjacent with three different vertices. Similarly, V3 is adjacent to V2, it's adjacent to V4, another circle, and it's adjacent to only V4 and V2. So now we will only see those vertices which are not in U but are adjacent to some vertex in U. So therefore V1 and V4 will be those vertices which belong to N of capital U, as they are those. So V1 is connected to V2 and V4 is connected to both V2 and V3. So they are a part of the set capital N of U, because they do not belong to you but are adjacent to some vertex in you. Now let us see another concept, that is subgraphs. So a subgraph is a graph which is, as the term suggests, it's a smaller version of the original graph. So how is it constructed? So let's see the definition. A graph G1 equal to V1 E1 J1 is a subgraph of a graph G2 equal to V2 E2 J2, written as G1 less than subscript S G2 if V1 is a subset of V2, E1 is a subset of E2, and J1 is induced by J2. So let's think of another definition which is much simpler. If you have a graph and you delete some vertice, suppose in this graph, as you could see, you opt to delete some vertex like V1. So corresponding to that, you also have to delete E1 and E4 because they don't make sense. So you have to delete E1 and E4. And so the graph which you are left is going to be simplified, and it's going to be just uh, V4, V2, and V3. And this is actually two different edges. So if you delete this vertex, now this is also a subgraph of the original graph. So either you can delete a vertex or you can delete an edge. Suppose I would delete E1, then the new graph that is formed is also a subgraph of the original graph. So when you delete a vertex, you have to also delete the edges which are incident with it, for obvious reasons, because an edge uh, cannot exist without the vertices it is incident to it. So obviously you have to delete the edges that V1 is incident with. So these are the two ways how you can obtain a subgraph from an original graph, either delete the vertice or delete the edges. So you can denote such a graph as G minus V if you deleted only one edge, or G minus U if you deleted a set of, if you deleted a single vertex, then G minus V, or G minus U where U is a set of vertices. Similarly, G slash E or G slash F where F is a set of edges. Now, G1 is an induced subgraph of G2 if E1 consists of all those elements of E2 whose incident vertices lie in V1. Now, what do you mean by an induced subgraph? So let's see an example on the next page. As you can see, there are three different graphs, G1, G2, G3. G1 is the original graph, G2 is a subgraph, and G3 is also a subgraph of the original graph, which you can verify easily. Now let us see about G2. Is G2 an induced subgraph? So the definition suggests that if G1 is an induced subgraph of G2, if E1 consists of all those elements of E2 whose incident vertices lie in V1. That means if you have some vertex in G2, then corresponding to it, the edges that should be, for example, as you can see here, G1, uh, can you all see my cursor? I am not sure if my cursor is visible. Hello?
Yes, sir, your it's cursor visible.
Okay. So basically, as you can see, this parallel edges. Uh, so basically, you don't have the parallel edges here. But in this case, you have V1, V2, V3, three vertices. And corresponding to that, all those edges which were present in the original graph are present here. So it's something like uh, if you have it's something like if you have those many vertex, if you are removing a vertex, it's obvious that you will remove the edges which are incident with it. But apart from that, if you remove some other edges which aren't necessarily removed due to the removal of a vertex, then that graph is no longer an induced subgraph. So here G3 is an induced subgraph, but G2 is not an induced subgraph, because here you see the graph G2 has all the four vertices, but we have removed edges without removing any vertice. So therefore, it's no longer an induced subgraph. But in G3, we removed the vertex, and corresponding to that, we removed the edges. So it's still it's an induced subgraph because we didn't remove an edge on itself. So I hope this example is
If we
intuitively clear. You
remove
don't.
diagonally opposite,
Well, if you remove the any of the parallel edges, then it's no longer going to be an induced subgraph.
if I remove two diagonally opposite vertices, then
If you remove two diagonally opposite, then obviously, if you remove the vertices, then you will have. Then I think you will be left with. Uh, I think you will be
just two
left with
points.
only. No, no, just not 2 points. Maybe these two vertices. If you are talking about removing, I'm not sure which vertex are you talking about. So if you are talking
Yeah, yeah,
about
yeah. Hmm.
these two, okay, then obviously you will be left with nothing but just two vertices.
So that would be a induced graph.
Yeah, that would be induced. And that's also going to be a trivial graph because it has no edges.
Yeah.
So let's come to a few definitions here. So a walk. So let me go to my journal so that I've drawn a few pictures so that it's easier for you. So this is a simple graph. And now what is a walk? So if you want to go, it's like walking through the edges of the vertex. You can think of the edges as something you can walk on, and any order, any way you want to go, you can go through the edges. So it's a sequence of vertex and edges. So I have given just an examples like okay, so this example is not a correct one because this was for the previous one. Ignore this. Let me simply write down V1, then E1, then V2, then E2, then V3. Then you can come back through E2 to V2. Then again you can go through E2 to V3. Then you can go through E3 to V4. Then through E4 to V1. Anyway, any sequence, you can repeat the vertices, you can repeat the edges, and that's what a walk is. Now, the length of a walk is kind of the number of steps or the number of edges you traverse. So even if you repeat edges, you will count them. For example, you go from V1 to V2 through E1 and V2 to V3 through E2 and again return back from V3 to V2 through E2. So the length of this walk is going to be 3. So this is a definition of a walk. And as you can see, vertices and edges can be repeated. Ignore this length. This is for an earlier example. Okay, let's see the next terminology. The length. As I said, the length of walk is the number of edges in it. Uh, a walk is closed if its first and last vertices coincide. So, for example, here, if simply the walk was, so here, whatever example I've given is a closed walk because the first and last vertices are same. So if you return back to the vertex you started from, then that is a closed walk. Otherwise, it is an open walk. A trail is a walk in which no edge is repeated. Let me go through the next three definitions, then I will show you the pictorial diagrams. A path is a trail with no repeated vertices, and a cycle is a trail with no vertices repeated, except the first vertex is same as the last. Let's see that. So as you can see, this is the graph. Now a trail. This is a trail. V1, E1, V2, E2. For some reason, wait a second. E2. This is E2. And so V1, E1, V2, E2, V3. This is a trail. So you are going from V1 to V2 and then to V3. There are no edges which have been repeated. And since, but necessarily that doesn't mean that vertices cannot repeat. They can repeat. But in this simple graph, you cannot repeat a edge if you don't repeat a vertex, because every two vertices are connected by at most one edge. You don't have more than one edges connecting two vertices. So you cannot repeat the vertices if you cannot repeat the edges. So since it is a simple graph, there are no parallel edges. So a trail also means that you cannot repeat the edges, but in general, a trail is simply where, you cannot repeat the vertices, but in general, you can repeat the vertices. For example, if we go to the figure at the beginning, uh, V1, let's write down a trail here. So V1 to E1 to V2 to E through E5 to V4, and then through E6 to V2. This is a trail because we aren't repeating any of the edges, but we can repeat the vertices. As you see, I've repeated the vertex V2, and so V1 to E1, V2, E5, V4, E6, V2 is a trail. Okay, let's come to a path. So a path is a trail where you cannot repeat vertices. And if someone says that you cannot repeat vertices, that automatically means you cannot repeat edges. Because if you cannot traverse through the same vertex twice, then obviously you cannot repeat any edge between them. So no repeated edges and no repeated vertices. So an apt example is this itself. So here you can see V1 to E1, V2 to V2 through E2 to V3 is also a path. A cycle. So a cycle is a trail with no vertices repeated except the first vertex is same as the last. So a cycle here is going to be V1 to through E1 to V2 through E2 to V3 through E3 to V4 through E4 to V1. So this is a cycle. It's just that only the first and the last vertex repeat. So that's a special trail. It's not exactly a trail because a trail says that you cannot repeat a vertex, but you can think of it as except the last vertex, all other vertex in the trail are going to be distinct, and just the last vertex will be same as the first. So that is why cycle is a special trail where only the first vertex is same as the last one. only the first and last are repeated. Okay. For a path or a cycle, we will often blur the distinction between the sequence of vertices and edges and the graph it forms. The graph that is a path on n vertices will be denoted as Pn. So I will show you in a figure what is Pn and what is Cn. So a graph that is a cycle on n vertices will be denoted as C of Cn, and a graph is connected if each pair of its vertices can be connected by a walk, equivalently a trail or a path. So let's see what these three terms mean. So first of all, let's understand what is a connected graph. So as you can see, this graph, which is drawn in green color with the vertices in blue, is a connected graph. Each pair of vertices in this graph have some walk. They have some walk which connect them. So therefore, this graph is a connected graph. And since it is a simple graph, just try to think of this simple logic that if there is a walk between every pair of vertices, then there is a path. So if I say that there is a walk from A to E, then there is also a path from A to E. So you can think of this as very simple, because when you say a walk, you may repeat edges and also vertices. So if you are repeating something, you can remove that. And if you remove all the repetitions from a walk, then that becomes a path. So therefore, if there is a walk, then there is also a path. And this holds only for a simple graph, because if that is not a simple graph, then uh, there is a difference in the definitions, and there you will find some contradiction or some counter example why this is not true.
Can you
So
please repeat
let's,
the path?
so I'm saying that suppose you claim that this graph, as you see, is connected. So the definition says that if each pair of its vertices can be connected by a walk. Now, I say that if it is a simple graph, then each pair of vertices, and also it is connected, then if there is a walk between any two pair of vertices, then there is also a path between those pair of vertices. Because in a walk, we do allow repetition of edges and repetition of vertices. But in a path, we don't allow either of them. So if you see in a simple graph, if we consider any walk from A to B that can have, like we can traverse from A to D, then D to A, then back to D, then again back to A. So there can be several repetitions. If we remove all the repetitions from any such walk, then that becomes a path. And so I claim that if there is a walk between A to B, then there is a path between A to B. This is, I think this is very simple to understand.
Yeah, true.
Yeah. So, okay, so this is, okay, I just will highlight that. Okay, so this is actually a disconnected graph. This complete setup is a disconnected graph, and you can see three different connected components. So AB is a connected component, GHI is a connected component, CDEF is a connected component. So the number of components is 3. So in these 3 components, all pair of vertices have some path between them. So therefore, it has 3 different connected components, but on the whole, it's not connected, because every pair of vertices do not have a path between them. Let's look at what is P4, C4. Means in general, what is P and CN. So let's see what is CN. So basically, it's a simple graph, which is a cycle on n vertices. So let's go back to the definition. So a graph that is a cycle on n vertices will be denoted as Cn. So we take n vertices and we make a cycle out of all those n vertices. So if there are 4 vertices, we make a cycle out of all those 4 vertices. So then that is called as C of n. It doesn't mean that we take 4 vertices and I've chosen wrong color. Okay. So it doesn't mean that we take four vertices and construct something like this and this becomes C4. No, this is not C4. This is C4. Because all the vertices should be involved in the cycle. You have to construct a cycle and only one cycle in the entire graph, which is consisting of all the vertices. So this is C4 and this is C5. Similarly, so C6, C7 you can construct. So let's see what is P4. So Pn, the graph that is a path on n vertices. So basically, you will take n vertices. So how will you construct a graph that is P4 or any Pn for any n? So basically, you take those many vertices and you try to construct a path uh, connecting all those vertices. So in a simple way, you can think of making C4 or making Cn and removing any of the edges, which gives you Pn. So basically, uh, it's basically a path on n vertices, and the length of that path will be n minus one. So that is how we can represent any particular type of graph like Pn. And what is K4? So let's see what is Kn. Basically, if you have some edges, then what is the maximum possible, if you have some vertices, let us say you have n vertices, and you want to see what is the maximum possible number of edges that you can draw, keeping it a simple graph. So basically, every vertex can be connected to every other vertex. So therefore, you will see that the total maximum number of edges a
Equal.
graph can have is going to be n into n minus 1 by 2. So that's how this is a complete graph. So a graph which is having all different vertices connected to each other is a complete graph, and it is represented by k of n, where n is number of vertices. So here you can see the number of edges is 4 into 3 by 2, that is 6, and therefore it is a complete graph. Okay, so let's come to the next term. I hope this is clear. So K4, I'm sorry, Kn, Tn, and Cn. These are the three different terms. And also we discussed about connected and disconnected graphs. Let's see what a complete graph. Okay, I just discussed it. And this is denoted by Kn. So it's a simple graph in which every two of its n vertices are connected by an edge. So if G is a simple graph, then the complement of G denoted by G bar is the simple graph on the same vertex set as G, in which two vertices are adjacent if and only if they are not adjacent in G. So this is very simple to understand. So as you can see here, this is the simple graph. And this is the complement of that simple graph. So I have just removed all those edges which were in the original graph and added all those edges which weren't there in the original graph. So it's simple like you take the complete graph and from it you remove all those edges which are in the original graph. So you remove V1, V3, you remove V1, V4, you remove V4, V3, and you are left with only V2, V4. So this is the complement of the original graph. So basically it is saying that in which two vertices are adjacent if and only if they're not adjacent in G. So if they do not have an edge in G, then they will have an edge in G bar. A simple graph is self-complementary if it is isomorphic to its own complement. So I have not covered this topic isomorphism, but I will provide the material to it. It's also very simple topic, and I will also try to discuss it at the end. It's also very intuitive. So let's skip it for now. At the end, I will try to discuss it. What is isomorphism? It's a very simple topic. Uh, so this problem is a good one. So suppose that G is a non-trivial graph. Non-trivial graph means that there is some edge and such that both G and G bar are connected. Prove that G has P4 has an induced subgraph. So this I would like you all to solve as an homework, not here because the solution is not so simple. So uh, you can note it down, but I will provide you the solution for this. So you can try thinking of this at the end of this session. So you can ignore the next two problems or you can do them. I will provide you the slides, but for that I need to discuss what is self-complementary. And for that I need to also explain you what is isomorphism. So if I'm able to do this, then then you can easily solve them. Actually, problem three is easy and I would like you all to come up with a solution in this class session itself. So let's see this last definition. So we call this lemma as handshaking. So can any one of you just simply prove this lemma that the sum of degree of all vertices is twice the number of edges in G, that is denoted by double mod. It's very simple. Like you can just think that
For example,
if,
yeah,
yes, continue. Yes.
for every edge, if we take 2 points AI and AJ,
Yeah.
so for every one edge, there is a two increase in the degree of the vertex.
Yeah, yeah. So every edge is, so even if there is a loop, we still count it twice for a particular vertex. So even that is counted twice. And if that is not a loop, we definitely will count it twice because an edge will be incident with two different vertices and both of those vertices will contribute, means the edge will get some, will be counted twice from those two vertices and therefore the sum of degrees is equal to twice the number of edges in the graph. And obviously the corollary is very simple. Number of vertices of odd degree is even because obviously the sum of degrees of all vertices is an even value. So number of vertices which are of odd degree have to be even so that they remain even. The sum remains even. Okay, so let's also come up. I have also another problem. This is the end of this slide, but I have another problem. So let's see. So basically, this is the problem. Let me just get it in the middle of the page. So yeah. So try to prove
So
that
we
for a
are
simple,
talking about,
this one, extra fun problem. Is it not visible?
yeah, it is visible in the what we discussed in the previous slide. So was that for a
Uh,
complete graph or for any general graph?
Handshaking lemma.
Yeah,
It is for any graph, whether it's
and,
complete or whether it's not complete. Means it's whether it's simple or it's not simple. Any graph will be having this true
and as well as the corollary.
corollary. Yeah, that's also going to be true for any graph.
Okay, fine.
So it's so corollary means that it follows, like it follows from this theorem. So it's something like it's obvious from this theorem, but we are stating for completeness. But there is nothing new from this corollary. Everything is in this theorem. Okay, so just try this problem that for a simple graph with more than equal to two vertices, at least two vertices should have the same degree and use something used in the last session. At least two vertices should have the same degree if it is a simple graph and it has more than two vertices, more than equal to two vertices. Think as how many possible degrees can a vertex have if there are n vertices.
N minus one.
Yeah, so obviously if it has only n minus possible values,
By
then
pigeonhole principle, we can say that.
yeah, pigeonhole principle, and we can say that they will have, and we are not considering zero, because if they are, means if you consider any of the vertices having 0 degree, then obviously the others, means you can just reduce it. Like if there is some vertex which has 0 degree, then remove that vertex, and now you have a graph which is of n minus one vertex, and still you can prove that this is true. And if you just keep on taking out the zero vertex degree, then you will end up with all vertices as 0 degree, and that's also going to prove this theorem, because we are just trying to prove that more
Yeah,
than equal. Yeah, so even zero will work, means it's not that. So that is why I am considering only from 1 to n minus 1 possible values and n edges. And if you consider some of it as zero, then you will also get two different vertices as 0 degree or something different, means you can be able to reduce the problem. So let's discuss a little bit of isomorphism. This is very simple. Suppose I draw a graph like this. I think I chose a wrong color, but let's go ahead with it. Yeah, so this is an graph. Now I will try to represent this thing in a very different fashion. Say I will do something like this, then I will make something like this. So I have drawn a very simple example, but you will have many complex examples. So on the, if you look at them, they still look a little same, but yeah, there can be many complex examples where they will not be looking the same. But as you see, I have drawn the same graph twice, but all that I have done is I've changed the structure, the way it looks like. The edges, I have just tried to, like, I've just thought of the edges as some strings, and I've just tried to play with those strings and place them somewhere and try to stretch them or try to place it somewhere else. So these two graphs are still the same, and they are called as isomorphic graphs. So what is self-complementary? So if I draw a graph and I get its complement, and they both are isomorphic to each other, that means both are the same graph, then this graph is called as self-complementary graph. So presently I don't have an example with myself to talk of a self-complementary graph, but I think it's not so tough to find. So the problems that were there, let's discuss that. Show that the order of a self-complementary graph is congruent to 0 or 1 modulo 4. So what is the, basically, as you would have seen, order is the number of vertices in a graph. So number of vertices in a self-complementary graph is congruent to 0 or 1 modulo 4. Before that, let's see one more observation. Uh, so if, okay, I guess I made a new page. Okay, fine. So suppose I make, okay, so if I say a simple graph, if I consider a simple graph and I make its complement, so what is the number of edges that it will have? So a complete graph of n vertices will have n into n minus 1 by 2 edges. And x is the number of edges in the original graph. The complement of it is obtained by removing those edges in the complete graph, which are in the graph itself. So the number of edges will be n into n minus 1 by 2 minus x. So when we talk about, so it's a very important problem in computer science, how to uh, how to prove that two different graphs are isomorphic. So there is no very easy way to do that, because we cannot easily tell that, yeah, this is how, we cannot try to reduce the two graphs to some simpler graph which is same. So let us see how we can check that to make our comparison easier. So obviously, if there are two isomorphic graphs, then they will have the same number of vertices. Also, they should have the same number of edges. Now, if a graph is complementary to itself, it is self-complementary, then it is isomorphic to itself. And they will also have the same number of edges. So x equal to n into n minus 1 by 2 minus x, or x should be equal to n into n minus 1 by 4. Now, obviously, x is an integer and n into n minus 1 has to be divisible by 4 so that x is an integer. So I hope it is now clear why the number of vertices in a self-complementary graph should be either a multiple of 4 or it should be of the type 4k plus 1 or 1 modulo 4. And the next part is construct a self-complementary graph of order n for every positive integer n congruent to 0 or 1 modulo 4. So basically, I'm giving you some n, some order n, some number of vertices, and you have to construct a basically a self-complementary graph. So can someone of you think how you can do this? I have just given you n vertices and you have to come up with a self-complementary graph.
Can you please give an example of for some lower order, for example, 3 or 4, because I'm a bit confused.
So you are not able to understand what isomorphism.
No, I can understand, but I cannot understand that graphically, the self-complementary. How can I draw it?
So let me think of an example. Let me think self-complementary.
Like for four vertices, we can have kind of like a Z shape.
Yeah, we can make something like 4 different vertices, and I think this uh, I think this should be a self-complementary graph, because if I take a complement, yeah, this is a self-complementary graph. So the complement of this graph will be this. So it's going to be this, and this. So and if you just flip this graph, you will see that they are the same graph. So yeah, these two are isomorphic to each other and also they are complementary.
What is the definition of two graphs being same?
So basically the formal definition goes like this, that if you can basically construct some mapping from this graph to this graph. So you have to, like, suppose this is 1. If I number the edges, say 1, I'm just confusing, 1, 2, 3, 4, these are the vertices. And these are the vertices. I consider some number, say A, B, C, D. So I claim that if I say that these two graphs are isomorphic, then I have to construct some mapping. So I will map vertex 1 to A, 2 to B, 3 to C, and 4 to D, or something like this. And I will also map the edges through each of these vertices, through corresponding edges through that vertex that I have mapped to from this original one. So if I map 1 to A, then 1 is connected to 2. Therefore, 1 is mapped to A, 2 is mapped to B. So if 1 is connected to 2, A should be connected to B, but it's not that here. So this mapping is improper. So you have to construct some mapping such that the edges from, suppose, x and y is edge. So that is how we construct. So the formal definition, I don't have the material. So basically I'm telling in a very crude language, but it's like you make a function. So phi of x is going to give you a vertex which is in this graph, and phi of y is going to give you a vertex which is in this graph. So if xy is an edge, then phi x phi y should also be an edge. If you can hold this true for all pair of vertices, for all edges, for all pair of vertices which have an edge between them, then they are isomorphic. So basically, checking this is not simple, and basically a simpler. So basically, it's not a very easy problem. It's an NP hard problem. Means you don't have a proper shortcut algorithm to do it. You have to basically go through possible mappings and go through and try to map it in some way. So you have to be, maybe exhaust all possibilities in the worst case, to check if the graphs are basically isomorphic to each other or not. So a simple way we can just try to eliminate is by checking the number of vertices, by checking the number of edges, or by considering some of the vertices, and seeing that basically, like if one is connected to, suppose I don't find any vertex in this graph where sub vertex is connected to three different vertices. So if that is not true in this graph or any of the vertex, so it's like something like doing it by common sense. Okay, so this is what is how we, this is the meaning of isomorphic graphs. So basically the question that I was asking is, if you can construct a graph, if I have given you some order n, so if you can construct a self-complementary graph. So is any idea coming to you so that we can discuss?
We can, I think, use a Cartesian system and then locate the points as x1, y1, x2, y2, and x and yn.
So
And
what you are saying? We have a Cartesian system, and
we have the points located as x1, y1, x2, y2, x3, y3.
okay, x1, y1, x2, y2, x3, y3 somewhere. And then,
No, no, no. I'm sorry. I got confused a bit. No, that
yes, so
no.
yes, basically you have n. So basically, so you can think some way that you have some complete graph. So basically you have several simple complete graphs, like you easily found no, I'm sorry, not a complete graph, but rather a self-complementary graph which is with four vertices. So is it possible that if we have something simple, we can keep on adding the vertices and edges to it and still keep it self-complementary, so that you can construct it for any n, because n is either 4k or 4k plus 1. So if you already have something of the order 4k, then you can add four more edges and still it would be 4k. Four vertices and still it would be 4k, and similarly for 4k plus 1.
But it's not an if and only if wala case, no?
What do you mean by if and only? Means obviously self-complementary graph can only have 4k or 4k plus 1. So it is not, it means if it has 4k, I'm not saying that it is going to be self-complementary if it has 4k vertices, but if it is self-complementary, it has to have either 4k or 4k plus 1 vertices.
Yeah, we have to only work with these kinds of, yeah.
Yeah, that's not if and means you cannot take any 4k vertices. So I think let's try to see what kind of solution we will get.
Is
Let's
it
go for
related to
example.
some kind of reflection or so? I'm just guessing.
Uh, Reflection, not really that way, but probably you're close to this. So let's see how we will proceed to this. So let's consider some graph which is self-complementary, and let's say that is H. So H can be any graph. Now what we consider is, we consider P4. What is P4? It is a path. So as I showed you, this is P4. So it is a path on n vertices and it has n minus 1 edges. So this is P4. Now what we will do is, we will join each vertex in H. Suppose I label this as V1, V2, V3, V4. So V2 and V3. So we will join each and every vertex in H. So remember, H is a complete graph, self-complementary graph already. So V2 and V3 will be connected to each and every vertex in H. So we call this operation a four-path addition. So ignore the term, but just understand what we are doing. So this is what we do. We just add the edges from each of the vertices in H to each of V2 and V3. So suppose there are n vertices in H, then we have added 2n edges, because each vertex will be will be connected to V2 and V3. Now the resulting graph is having VH plus 4 vertices. So basically, as you see here, the number of edges, the number of vertices is H plus V1, V2, V3, V4. So VH plus 4 is the number of vertices. So since H is already a self-complementary graph, then if n, which we got, was 4k, then if we find VH to be of the form 4k, then we can keep this value as still 4k. So it's like by the principle of induction, that if I have a graph which is self-complementary and has four edges, or let's say 8 edges or whatever, 12 edges, then I can make something of 16 edges, 20 edges, 24 edges, so on, and reach the apt value of n. So is this graph self-complementary? Can you check? Is this graph self-complementary? H is already complementary, and V2 and V3 were the ones through which we drew edges to each of these vertices in H. So you need to think why this is a complementary graph, self-complementary graph.
So we have added only 2n edges.
No, we just haven't added 2n. We have added like not 2n. Let's say VH is the number of vertices in H. So if E was the number of edges in H, then we have added E plus twice of V of H plus
Yeah, that's what I mean.
plus three more edges, that is V1, V2, V2, V3,
Oh,
and V3, V4.
okay, yeah.
So can you think of why this particular graph is self-complementary?
Hello.
Yes.
Can I answer if I'm not a first year?
Yeah, you can answer.
The original graph, H was self-complementary, and the paths we added to it was also a self-complementary graph. and the two n parts that connect every vertex to the two vertices from the path um, can be like they're like analogous to the path that we should connect. I mean, V1 and V4 could connect to H, and that would be its complementary graph. I mean,
Yeah, so basically, when we take the complement, then V2, V3 will not be anymore connected to any of the vertices in H. And then V1, V4 will serve the function of V2 and V3. And so then V1, and also we can see that H is already self-complementary. So H bar will also be, means it is going to be complementary, means it's going to have the same number of edges, same number of edges as usual. And V1, V4 will be connecting itself through H. And then in this V2, V3, V1, V2 and V4, V3 will vanish away. And we will have the edges V1, V4, V1, V3. So basically this will become V1, V4, V1, sorry, not V1, V2, but rather V1, V1, V3 and V4, V2. So it's basically the same. So if you bring V2 here and V3 here, it's the same thing. Like V2, V3 became V1, V4 and V1, V4 became V3, V2 or whatever. So this still remains self-complementary. So we can keep on adding vertices and uh, like this, and we can appropriately construct. So for example, if we need 4k plus 1 vertices, then H can be made, means H may have 4k plus 1 vertices already, and we add 4 to it. So this still will remain 4k plus 1 and keep on adding 4 unless we reach the appropriate amount n, and same for any other graphs, like yes. So, any doubts before we close the session? I just ask you all to try this problem. If you haven't, I will share these slides, but it's just asking you that if G is a non-trivial simple graph, is that both G and G bar are connected. So G and G bar are connected, prove that G has P4 as an induced subgraph. Means that basically G and G bar are connected is, it's simple. I just explained you what is the meaning of connected. And P4 as an induced subgraph. Induced subgraph means that um, I can obtain P4 just by removing some edges of G. I don't need to remove any, I just can obtain P4 by removing some vertices of G,
Yeah, I get.
and I don't need to remove any edges unnecessarily from G. So P4 is an induced subgraph. So try to think of this problem.
Can you send some material of self-complementary? Actually, I did not get the definition properly.
Self-complementary. Basically, yeah, I have a book. I will send it. But what didn't you get? Like, I understand that. What means? Are you not getting a example in your head? Not able to explain some example in your head? You can ask so that I can try, or
Y-
something.
Yeah, I did not get the formal definition very properly. For smaller orders, I can get it for 2, 3, 4, 5. But for general and it's not, I'm getting. I just want a formal definition and then want to approach it.
Yeah, I have actually. I have basically I removed those portions because I didn't plan to cover isomorphism, but I do have those because they were all means they were in the original slides. This one is a modified one. So yeah, they were there.
Okay, if you do that, so that would be great, please.
Yeah, I will just post it now. You can look it just now after the session. I will post the original one. Yeah, it's having this in a very formal and nice way. And do try to Google things also, because in Google you will find a lot of resources connected related to this, and lot of examples you will find. You can easily see the examples. There can be YouTube videos which explain how you can check two different graphs are isomorphic and so on. So yeah. So fine. I think we can close the session here. So any doubts before we close?
I had to ask one thing.
Yeah.
The construction which you gave right now for constructing self-complementary one, I mean, for a given number of vertices of 4k or 4k plus 1, do all these self-complementary graphs fall under this construction? Like, can this construction construct all these self-complementary graphs?
That's a very good question. No, I don't think that it can construct all different self-complementary graphs. Uh, because this is a way just to make, means we can make at least one graph. That's what this way suggests us, but not all, obviously. I can easily find examples. I think you can even find examples which can't be obtained through this method, but they are self-complementary to each other. But I think I'm not finding a very good proof. I'm just saying it in the air, but I don't have a good proof. Let's be a graph which is self-complementary. Self-complementary. I think of an example which cannot be applied. Mm. Is any example coming to your mind? Because nothing is coming to my mind.
No, even nothing was coming to my mind, so I mean, I conjectured like it should be the case.
According to me, it should not be. So,
Yeah,
मतलब just
so
the intuition.
what do you say?
Just by intuition, I feel it should not be because it will actually limit it very much. I do not know the proof actually. Sorry.
Is it the case that maybe for a particular complete graph, uh, there are only, I mean, if the number of vertices of a complete graph increases, would the number of self-complementary graphs also increase?
The number of different types of self-complementary graph for a given vertex, number of vertices n. Yes, obviously, if you increase the number of vertices, then the number of different self-complementary graphs which can be obtained will also increase.
Yeah.
Actually, they will increase by at least double because the example you showed that you can actually connect V1 and V4 as well, and that will still make the construction valid.
Yeah, yeah. V1, V4. No, no, not no, no. We cannot connect V1. Can we connect V1, V4?
I mean,
V1,
like
V4.
you showed that we connect all the vertices of H with V2 and V3. So instead of V2 and V3, if we do that same thing with V1 and V4, the construction is still valid.
What made you think like I don't? If you construct and you connect V1, V4, then is it still self-complementary?
The example that you showed on the graph was actually not self-complementary, the P4.
Which one? Are you talking about this one, Z or something? Or
In
are
the
you
last
talking about
one,
the,
the
yeah?
P4 that you showed. No, that is Z is the in the last example. Yeah, here.
Are you talking about this? Yeah.
Yeah, this should not be self-complementary, I think so.
Why do you think this is not self-complementary? Like, I gave a proof. Like, basically, you are having some edge and you are having some vertices. Like you have path P4. There is edge 1, 2, 3. There are vertices edge 1, 2, 3, 4. Then 2, 3, you connect to all the vertices.
No, no,
Uh,
my question is different. My question is different. The example
yeah,
of
what's your question?
P4, the example of P4 that you gave is I think so wrong. What you took as P4 is not, I think so. It is not complementary, self-complementary.
Are you talking about this?
Yeah, the P4 here that you took.
No, no, I'm not saying P4 is self-complementary. I'm just saying that this entire, I'm sorry, yeah, I'm just saying that this entire thing is self-complementary. Like, uh, then if I take the complement of this, what will happen? The edges will start getting, means they will start from 1 and 4, and 1 and 2 will not anymore exist. So basically edge and 1, 2, 3, 4. And so now the edges are all connected to 1 and 4. And basically earlier you had an edge between 1 and 2. In the complement you won't have an edge between 1 and 3, 1 and 2, rather you will have an edge between 1 and 3 and an edge between 2 and 4. Then so basically all those edges that were not there, so you will have an edge between 1 and 4. So this entire thing is self complementary, means this is the complement of this one.
So
I
for
didn't
this,
just
P4 does not need to be self-complementary.
No, no, not P4. Actually, P4 has been taken wisely because we want it to, we want that n remains either 4k or 4k plus 1. So that is why P4 has been taken and a construction has been made so that we can find out any self-complementary graph for a given n.
Okay, okay, fine.
I don't know if it need to be the case, but in this particular case, P4 would be self-complementary because it's an isomorphism of the Z graph. I mean, the one that looked like a Z, I think.
It's a self-complementary graph. Yeah, P4 is also self-complementary. Yeah, because as you can see, this and this means these two are self-complementary to each other. So P4 is also self-complementary.
Okay.
But I need to get some proof for whether we can construct all self-complementary graph through this method or not. And I will also share this. I actually have a proper way of, since I have a PDF which explains this method, so I will share that also. So you can go through this, through that if you still have some doubts. And yeah, try to solve that problem. And if you want, post the solution to that problem which I've given here in the chat itself, and I will try to see and reply to it. And also this problem whether all graphs can be constructed through this method. So I think there are no more doubts. So I think we are closing this meeting. So thank you all for attending this.
Thank you.
Basically, I think only three of you I think are present. So could you give some feedback of how the session was? Quick feedback so that we can improve upon, because I should have made a Google form, but yeah, just three people. I don't need a Google form. Just a short feedback of how the session was and whether we can improve in any way or not.
According to me, I think if a bit more problems and bit more kind of interactive, although it was really good, but kind of more.
Yeah, basically we had problems, but we removed it because we thought that it could be getting little complex. And yeah, so basically that is why we decided to not go with problems. So next time obviously we'll come up with problems. We have a lot of problems with us, and I would be posting the book itself, which has a lot of problems. So next time we will come with problems. This time, because last time when we had the session, we saw that people weren't so comfortable with the problems. So we decided that this session we will keep only for the basics, and next session we will come for only problems on graphs.
Great. Okay.
Yeah, so next session I think it should be only on problems. Fine then. I think we can leave. Thank you.
Thank you.
Thank you very much.